So we're going to jump into section 3.9, which has something to do with linear approximations, and the way that I want you to think about linear approximations using nice, easy lines. I'm saying nice because lines are easy. We know their equations. They have a constant rate of change. Using nice lines to approximate not nice curves. I'm just using the word not nice as an antonym of nice. So we know lines, we might not know some of these other curves. So the motivation for the problem kind of starts like this. If we were given some function f of x was equal to e to the power of 2x, what the heck is f of 0.01, especially without a calculator? So what I mean is, like, how would I figure this out? F of 0.01, so e to the 2 times 0.01 power. So what is e to the 0.02 power? Well, I have no idea, especially without the use of a calculator. I can make some guesses, right? I know that f of 0, I can plug in 0 really easily here. And I can get e to the 0, which is just 1. And I know that f of 1 would be e squared. So I could do, like, whatever e squared is, so like 2.7 times 2.7. So somewhere like 7.5, somewhere in there. So I know that my value, f of 0.01, would be somewhere in between those values, again, because we know e to the x is always increasing. But I can't get too much further than that. So what we want to do is help use things that we know, like f of 0, to find information about things that are really close to it, like f of 0.01. So the way that we're gonna come back to this problem in a second. We'll actually answer it in a moment. But what we're seeing here is that sometimes evaluating functions is really hard to do, especially if we don't have a calculator. There could be many reasons for them. Maybe it's too hard to evaluate. Maybe we don't have a calculator. Maybe we just don't know what we're doing yet. We haven't learned it, so on and so forth. So to solve that problem, what we're going to do is we're going to use easier functions that we do know how to use to approximate what the value should be of that harder function. It's a general outline. So the way we're going to start with a nice function, a nice curve that we know really well. So we're first going to start by looking at the basic parabola, y equals x squared, or in this case, f of x equals x squared. So I have that prepared on a graph over here. Now, just for the sake of it, we're going to say 1 point, and I've labeled that point as a f of a, because again, it doesn't really matter what point we're looking at. I'm just choosing this one to begin with. What we're saying is, if we zoom in really, really, really close to this, as I zoom closer and closer, that simply just looks like a straight line. I know it's not. If I zoom out and put it in perspective, it's clearly not a straight line. But when I zoom in very, very, very close, it's a straight line. So when we zoom in close enough to most curves, they look like lines. Well, that's wicked. Well, what do we care about that line, right? So what I have here is I've zoomed in, or I'm going to zoom out a second, is I'm going to go ahead and just plot the derivative. We know what the derivative of x squared is. So I'm going to plot the derivative at the point that I've labeled. So there it is. That derivative is now in green. So we can see that the derivative is tangent to the point at a. So it's tangent at, in this case, a is 2. We know what f of 2 is. We can see that the tangent is right there. Now, if we zoom in on that point, closer and closer and closer, what you see is the green line. The green line is actually the tangent to the function, not the actual function itself. Now, if I remove the tangent line, it's just the red line. It looks like they're just right on top of each other. Now, they're technically not, right? We can see as we get farther away, they do get farther and farther away from each other. But right around the point that I started at, really close to that point, there's almost no difference between the original function, which you're seeing in red, and the tangent at that point, which you're seeing in green. So why do we care about that? Well, that's our first observation. So like our room for work here. So like the first thing we notice is that around a point like a and f of a, the function looks like the tangent line. They're almost inseparable at that point. Again, let's see that again. So here's our point A. The red is the curve itself that we've zoomed in on. And the green now is the tangent line at that point. And if we're close enough, can't tell them apart. So at this point, I'm just going to take a quick picture of this and put it into our notes. Now, why do we care about that? Well, if it's just a line, we know so much about lines. So I'm going to go ahead and put in the picture of the graph that we were just looking at. And again, this is very zoomed in. Let's just look at a certain portion of it. Let's just look at that part of it. Well, if what we're saying is that this line right here is really just the tangent line, well, we can write an equation of a line in point-slope form. So point-slope form, I'm going to start with y minus y1 is equal to m times x minus x1. And we're just going to start changing some notation here. So we need a point that we guarantee is on the line. Now in this case, we're trying to figure out like what's going on right here at A. So we know the point A is on the line. So the output, I'm going to replace with f of A. Right, so we're using this point because it's on the line. So then the x value is just A. Now, m is the slope of that line. Well, the slope of the line is just the tangent line. So in green, this slope is going to be the point of tangency of A. So what is the derivative at A? Well, that's the slope of that line. And then over here, we still have f of A. Now y, I'm just going to replace that with function notation just so it all looks a little bit better. So I wrote the equation of this line in green. It's f of x minus f of A should equal f prime of A times x minus A. And again, what we're saying here, just kind of going through that, is we have a point on our curve. We can't see the curve is in red, but what we notice is if we look at a point on the curve, the point of tangency is also on the tangent line. That's by definition of tangency. A and f of A is on the original curve, and it's the point of tangency. So the point of tangency is on the tangent line, so that's why we used our point A and f of A. And we know our slope, well, the slope is the derivative. So the derivative of our value at that point right there would be the derivative at f prime of A. Now that's it. That's what we're saying. What we can do now, I'm just going to copy that over. So we had f of x minus f of A should equal the derivative, which is the slope, times the point. Now if we just rearrange this, f of x would equal, so I'm going to add f of A to both sides. I'm going to put f of A first. So it would be a positive f of A, and then we would add f prime of A times x minus A. And this is what we actually want to conclude. So what this tells us is, first of all, this is the equation of a line. So we've used a local linearization, meaning we started at a point, so some local point. We started at that point and we looked really, really, really close to it. So we're getting local. Think of local as one point compared to global, which would mean the entire graph. So we're looking at one single point, and at that point we noticed that we could just estimate the curve with a line. So we wrote the equation of that line right here. But if we just rearrange the equation of that line, we're able to isolate f of x. So what that tells us is the value of the original function can be approximated with some other value a. So we would take f of a and we'd add the derivative of the function at a and multiply that by x minus a. Now a here, why do we care about a? A is a fixed point, but a is a point that's quote unquote nice. So we can use a point we know to estimate one we don't. So this is your main formula. We're going to go see that in action right away. So this was the original example that we were talking about. How would I figure out what is some crazy exponent of e without a calculator? The idea here is I know some values of this function. I can easily plug in 0. We kind of started the video like that. F of 0 would simply be e to the 0, which is just 1. I know that point. So I'm going to go back to my graph and just kind of type in this function. So I'm going to create just a new graph here. I'm going to create our function f of x, which is going to be just e. So I'm actually going to write it out loud. F of x is going to equal e to the 2x. Now, what I'm going to look for here, so e to the 2x. Now, I'm going to zoom in on the point 0, 1, right? So if I'm just going to do f of 0, which we know is 0, 1. Now, if I zoom in on that, and I get close enough to that local point, so this local point that I know, it looks like a line. So instead of trying to use that crazy curve, what I can do is just find the equation of this line here and just use the line to approximate it, because the point of the input of 0.01 is very, very, very close. Let's just kind of put that on the graph. Let's find out where is f of 0.01. It's so close to the original point. I'm going to label it here as a point. So 0.01, comma 0.1. So we make it a point so it shows up. What we can see is that that point is like literally so close. Like, I don't even know how to zoom in close enough to see it. But it's so close to this point, wherever it is. It's so close to the point that that line is going to be a fine approximation, right? If I look at these two right here, it almost looks like the thing connecting those two is a line. They're very close to each other. So that's what our idea is. Rather than trying to evaluate the function itself at 0.01, let's approximate this with a line. And that's where our kind of like formula came in from before. We said to approximate the original function, or the original value at the function, we would take the function value at a point we know that's very close to x, and then we'd simply, and again, maybe I'll go back and show you what I'm referencing. Just referencing this again, our main formula, and then we're going to add the second part here. So we have the value of where we know, so this is where we're starting, and we're going to add a small amount of change right around that point. So in this case, we're trying to find 0.01. Now, 0.01 is close to 0. So that's why we can use 0 as our a value. And we know f of 0, we said up top, that was 1. Now, we'd have to find the derivative of our function at 0.0, so we can quickly go find that derivative. We know the derivative of this would be e to the 2x times 2. So the derivative at 0.0 would be e to the 0 times 2. And we'd multiply that by x, and our a value is 0. So f of 0.01 should be 1 plus, what do we have here? We have 2, right, times x. And our x value is, I should have replaced already, is 0.01. I can erase that. So our x value is 0.01. That's really easy to do. This is just 1 plus 0.02. So I would say that it's probably not perfect, but I used an easy line, a much easier formula to approximate f of 0.01. So that's why I'm going to use the approximate symbol. But f of 0.01, according to my linear approximation, should be about 1.02. Now, if I go to my calculator right now and actually type in e to the 0.01, or sorry, input this, so e to the 0.02 technically, my calculator does tell me it's exactly equal to 1.0202. So summarizing, we need to know a point that's close to the x value that we're looking at. So what we're saying is, and just as like a summary, I'll go to the next example first, actually. What we're saying is we think that we could use our line to approximate this actual function value. We could just use this formula instead. So we got 1.02, which was pretty close. Let's look at another example to see it. So this is just the general term. So like if we have some function, which is e to some exponent, so some power of x, how would I be able to approximate that? And again, like I just don't know what that is. It's going to be too hard for me to find all these crazy exponents. Now, there are some things I might know, like I could definitely probably do f of 0, because that's going to be, e to the 0. I could definitely do f of like something like 1 over k, because that would be e to the first power. But if it's anything else, like even if k was like 1.6, I'm just not going to be able to do that. What is e to the 1.6? Like what I don't want to use this function. This function is very complex. So instead, we could approximate an easier function. So for example, if I wanted to approximate f of x, instead what I could do is I could take the value of f at some point that I know, and I would add our little bit of change at that point that we know times x minus a. Now here, since we don't know what k is going to be, we're not quite sure what a is. Now just remember that a needs to be close to x. So what we could do is we would just simplify our rule and say f of x is equal to f of a. Well, let me rewrite that a little differently, actually. Yeah, let's just be clear about this. Let's say a needs to be close to x. So let's go back and just use this example. Let's say we're near 0. Let's just look at that example. If we're near 0. So if we're near 0, well, we know like the thing that could be close to 0, if x was 0, well, a is close to 0 too. So anything that's around 0, we can use for our a value. Well, I know 0, so I'm going to plug in 0. Oops. So again, the a value is what we know, and we need to have a value we know that's close to the area we're looking at. So if we keep going here, we'll summarize at the end. F of x should equal, so f of 0, we said before that was just 1. E to the 0 power is 1. And we know the derivative of e to the kx would be k times e to the kx. And then we'd multiply that by x minus 0. So in general terms, what we'd see is that, now this is important. So this is our final kind of generalization. Sorry, that's a plus sign, not a minus sign. So what we're saying is, I'm just going to write this on the next page. Well, I'll write it over here. So around x equals 0, because that's where we kind of started the problem. I said, well, we got to be around somewhere. So we pick a point somewhere that we know. So around x equals 0, our function, e to the 2x, can be approximated by this other function, which I'm just going to change the letters right now to g. And what we'd see here is that this line is way easier to work with than this. Now the huge caveat here is that only works around x equals 0. If we changed it and said, well, what would happen around x equals 1? Let's look at that real fast. So if we're given that same function, f of x equals to the kx, But this time we're asking ourselves around x equals 1. Well, our formula would be the same. F of x would still equal f of a plus f prime of a times x minus a. But the idea here is if we're around x equals 1, then we need to know a point around 1. So in this case, I'd probably use the a value of like 1. I'm just saying it's going to change the function. I don't know what k is yet, but the idea is if I wanted to find f of x, maybe I'd use the point 1 to find that. Now, if I use the point 1, what we're obviously going to see is that that's going to change the formula. And sometimes it doesn't change it in any nice way at all. Like if I did k times e to the 1k, that doesn't necessarily make it nicer. What we can see is that the approximation at this point is different than around 0. So it's really important to remind yourself that when we're looking at these approximations, we're given something that we need to be around. And we can only approximate within a certain distance. Because again, if we go back to a graph like this, and I open up the original one we started with, what we can see is around the point, yes, there's some definite, there's a definite overlap. Like they definitely look the same right here, because I'm around that point. But if I get too far away from that point, so I'm not close enough anymore, that approximation is actually not really good. Those lines are really, really separate from each other. So it's really close that they're near each other. It's really important that they're near each other. So one more example. So sine of x, that's a curve, right? So let's look around. Let's do x equals 0. So around x equals 0, we obviously know what it looks like, and we can evaluate some stuff here. Like we have the sine function, right? So we know it looks something like that, but what's happening just right here? So again, to visualize, we're going to go to our graph here. We'll start a new graph. We're going to type in the sine of x. And I'm going to zoom in really close to 0. What we can see here is I get closer and closer to 0. This just simply looks like a straight line around that curve. Now, it's not really a straight line, but in that area, if I get close enough to 0, it is a straight line. So I'm just going to put that picture in so we have it with us and say, okay, so around x equals 0, we don't actually need to use the function sine of x. Maybe we're not super happy about trigonomic functions, or maybe they're difficult to work with. But around x equals 0, it's just a straight line. So what we're going to say then is around x equals 0. Now, what's good about around x equals 0 is I know the sine of 0. I know the sine of 0 is 0. So my reference point A is going to be 0. So I could approximate f of x with a different function, which is usually easier to work with. And it's usually a line. So what we do to find out our new f of x, I'm just going to put in green, we would take the original value of something we know, and we'd add our little change, right, the rate of change around it. And in this case, we're going to substitute a and all these values here. So our function will be approximately equivalent to the sine of 0. Now the derivative of sine is cosine at 0 times x minus 0. Well, there's some good things here. The sine of 0 we know is just 0. The cosine of 0 we know is 1. And x minus 0 is simply just x. So we summarize and say our function f of x around x equals 0, it's only around there, we could replace this as 1x, or in other words, just x. Now, what does that mean? Let's look at some examples using a calculator real fast. So the sine of x is approximately equivalent to x around x equals 0. So let's try a couple. So like the sine of 0.01. If we go into our calculator and actually type that in, of course we're in radians, the sine of 0.01 on my calculator is 0.00999. If I would have used the approximation of x, I would have gotten just 0.01. And those are pretty darn close to each other. Let's do something else pretty close to 0. Like let's do negative 0.01. Let's see what that does. So the sine of negative 0.01 on my calculator comes out to be negative 0.0999, obviously. And if I put in the x value, just using the approximation, it would have been negative 0.01. Those are really close. Now what we should see is this approximation is only good around x equals 0. So if I try to do something that's really far away, like the sine of 2 or something like that, if we're talking about small changes, 2 is nowhere near 0. So on my calculator, the sine of 2 radians comes out to be 0.909. If I try to use the approximation of x, these are nowhere near each other. They're bad because 2 is not around that one point that we knew. So our approximation is only good around the points we know, and there's a finite limit to what we actually have as an approximation. And as our final thing about that is the approximations we have are only good within a certain distance, and that distance we're not going to cover, but we have to understand that we might be wrong. And the way that we can be wrong is easily seen using just like different concavities of the graphs. So I'm just going to draw 2 separate graphs, one concave up, one concave down. So like what we're talking about is instead of using the curve to find our value, we could just look at a point and realize that at that point, the tangent line, which I do pretty terrible, the tangent line is a pretty good approximation within this certain area. If we get outside of that area, it's not a great approximation anymore. But if we're in that area, it's a pretty good approximation. Same thing over here. If the curve was concave down, if I have some point here and I want to find the value at that point, well, I could just look at the tangent line and say that the tangent line is really close to the original curve within a certain neighborhood. So like if I'm in this area, that line actually does a pretty good approximation of the curve. But what we're noticing is that if our graph is concave up, the tangent is below the curve. So our approximations are probably going to be a little bit too low if we are going to be off. So I'm just going to write down the underestimate. If we get too far away, we're more likely to be underestimating because our tangent line is below the original value. Over here, what we see is it's concave up. And if it's concave up, the tangent is above the curve. So if we get too far away from that point, like if we're way up here on our line, that's going to be an overestimate because our tangent line is always going to be above the curve. So if we get too far away, and I'm just going to draw a picture of that a little more zoomed in. So we're saying is if we have some curve like this, and I drew a tangent line at a certain point, like here's my point, and here's my tangent line. If I zoom in on just that part of it, well, let me redraw that tangent line a little bit better with just one. So there's my tangent line over there. Now, if I zoom in on that, which I'm going to try to take a picture of just really close to that. So if I zoom in, what I notice is around that point, whatever point we start at, so like right there, whatever point we started at, the approximations are pretty good along a certain aspect of it. But if I get too far away, like way over here, I'm more likely to underestimate. Or if I'm way down here, the value here is likely to be lower than what it should have been, right? The value of the black curve right here is probably way up top there. So I'm below it. So if I get too far away, I have an underestimate. And the argument works the same for the overestimate. The last part about that today is we do have an underestimate and an overestimate. So at times you might just want to ask, like, well, what is our error? And we know how to calculate the error. We know that error just in general is the actual value minus our approximated value, whatever we got it to be. So the way in section 3.9 that we'll kind of annotate that is the error on our function. So the actual value that we're looking for is the actual value of the function, f of x. And then we'd have to subtract whatever we use to approximate that function. And we know from before that we can approximate f of x by taking f of a and adding f prime of a times x minus a. So if we just kind of rearrange with algebra and make it all one term, to find the error, we would take our actual value. So we'd have to figure out what it really was, and then we'd subtract f of a, and then subtract f prime of a times x minus a. And that's me just obviously distributing the negative there. So this defines our value. Now the last part that I'm going to talk about that comes from the textbook is not super useful in what I'm going to make you do every single day, but there's this cool fact that shows us that the limit, if we look at a limit, this limit should approximate to 0. I'm just going to draw a zoomed in version of a curve real fast just to quickly talk about that. So what we're saying is if we have a certain point, we're going to look at a point that we know. So here's A. So the point A is like right here. So this distance right there is the distance between the graph and the value. So that distance is f of A. Now, if we look at a tangent line, I'm going to actually draw in a line with a line here. So I'm going to draw on the tangent line at that point. Right? Now, we're trying to use the value at the point we know, which is A, to approximate the value at a point that we don't know. Whatever that point is, I'm going to be x. So the distance here, this distance is x minus A. Now, we're trying to approximate it on the tangent line. And now I know that that approximation is not perfect, but we can see a few things here. This red segment will be f of A, right? It's the same height over there. And then we added a little bit more, which was, you'll be able to see that's going to be the change. I'm going to write that as f of A times x minus A. That's the change. So what we're looking at then is how far off are we? So the error here is going to be the distance between our blue tangent line and the black original curve. So our error, whoops, is right here. It's that distance. This is our error. Now what this limit says is as x gets closer to A, so as I were to take, I'm going to draw this in yellow now, or maybe I'll do another x. If I were to move this over, we'd have this point here. So that's our new x, so like x2. And then we'd still have that distance to bring us to the original A. And then we'd have the next distance to our tangent line. What we can see now is that the error there, which I'm just labeling as E2, just as our second error because we've moved x over, that error is smaller. Now what we're saying here is if we compare those two, the distance between x and A, and then the distance that we're wrong, this is going to come to 0, which means e to the x gets closer to 0. In other words, it gets closer faster than x minus A, because we have a fraction that's going to go to 0, and we know that a fraction is only going to go to 0 if the denominator is essentially really small, and the denominator is really big, and the denominator is really small. So it's just a nice fact, and it kind of proves that this is always going to work. If we take the points that we don't know and get closer to the point that we do know, that error should obviously go to nothing.